Section 20 of the Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 2, edited by Francis Rolt-Wheeler. Geology. Chapter 11. Structural Geology, Part 1. Structural geology in many ways is the most intricate of all the divisions of the science, for the reason that all the various factors come into play. Thus, while it deals with the substances of which the Earth's crust is composed, it is far from being merely descriptive. It must at the same time present as far as possible the causes of their placement and the forces which have gone to make up their structure. The object of structural geology is to learn not only the agencies which have produced the structures and the way in which they operated, but also the successive steps by which the rocks originated, the order in which they occurred, and their geological date. The distinction between a rock and a mineral is not always an easy one to grasp, yet it is essential that it should be so. A rock is any extensive constituent of the Earth's crust, which may consist, though rarely, of a single mineral, but in the great majority of cases is a mechanical mixture of two or more minerals. A rock thus has seldom a definite chemical composition or homogeneous internal structure. An examination with the microscope almost always shows that a rock is an aggregate of distinct mineral particles, which may be all of one kind, or many different kinds in varying proportions. Geologically, incoherent masses of sand and clay are regarded as being rocks, quite as much as the hardest granites. The igneous rocks wherein heat is the chief factor in their making, as the name shows, are truly primary rocks, in the sense that it seems that all others have been made from them. The particles of matter now composing sedimentary and metamorphic rocks have been changed so often that in many cases the relationship to the igneous rock is not easy to trace, but it is there. As geology is primarily a historical study, the most logical scheme of classification is obviously one that, so far as possible, is genetic. That is to say, one which expresses in brief the history and mode of formation of the rocks. This genetic principle would suggest the division of all rocks into three primary classes or groups. A. Igneous rocks, those which were melted and have solidified by cooling. B. Sedimentary rocks, laid down underwater by mechanical, chemical, and organic processes. And C. Metamorphic rocks, which have been profoundly changed from their original sedimentary or igneous character, often with the formation of new mineral compounds in them. The rocks of earliest times, called igneous, have a deep-seated origin and have either forced their way to the surface or have cooled and solidified at varying depths beneath it. They were the first to be formed, and all the others have been derived, either directly or indirectly, from them. The products of the chemical decomposition or mechanical abrasion of the rocks have furnished the materials out of which the sedimentary rocks were formed, at least in the first instance. The igneous rocks are massive, as distinguished from stratified, and though sometimes presenting a deceptive appearance of stratification, may always be distinguished from the truly stratified rocks. Characteristic differences appear between those igneous masses which have solidified deep within the earth, called plutonic, and have been brought to light only by the denudation and removal of the overlying rock masses, and those which have cooled at or near the surface of the ground, known as volcanic. In order to determine the circumstances under which the rock was formed, the texture of a rock must be observed, and hence great attention is paid to it, and in the igneous group 5 principal types of texture will be found. 1. Glassy, a glass or slag without distinct minerals in it, though the incipient stages of crystallization, in the form of globules and hair-like rods, are often observable with the microscope. When the glass or slag is made frothy by the bubbles of escaping steam and gas, the texture is said to be vesicular, scoriaceous, or pumiceous, according to the abundance of the bubbles. 2. Compact or felsitic, characterized by the formation of exceedingly minute crystals, too small to be seen by the unassisted eye, giving the rock a homogeneous but stony and not glassy appearance. 3. Porphyritic. In rocks of this texture are large isolated crystals called phenocrysts embedded in a ground mass, which may be glassy or made up of small crystals. They have usually solidified near the surface of the ground. 4. Granitoid. In this texture, the rock is wholly crystalline without ground mass or interstitial paste. The component grains, which may be fine or very coarse, are of quite uniform size, and as the crystals have interfered with one another in the process of formation, they have really acquired their proper crystalline shape. They have solidified slowly and at great depths. And 5. Fragmental. This is represented by the accumulations of the fragmental products ejected by volcanoes, agglomerates, bombs, lapilli, ashes, etc. The texture of an igneous rock is determined by the several factors which affect the molten mass during consolidation. Of such factors may be mentioned the chemical composition, temperature, rate of cooling, degree of pressure, and the quantity present of dissolved vapors and gases, which are called mineralizers. Chemical composition determines the fusibility of a rock at a given temperature. The effect of chemical composition upon texture is seen in the rapidity with which the less fusible rocks chill and stiffen, and therefore the greater frequency with which they form glasses. Hence, very rapid cooling results in a glass, but the microscope reveals the incipient stages of crystallization in many of even the glassy rocks. A somewhat slower rate of solidification produces a cryptocrystalline rock, and successively slower rates bring about the porphyritic, microcrystalline, and granitoid textures. Pressure is of importance in preventing the rapid escape of the vapors and gases contained in the molten mass, and hence frothy, scoriaceous, and vesicular textures cannot be produced under high pressures. The mineralizers, such as steam, hydrochloric acid, and other vapors, determine the crystallization of many minerals which refuse to crystallize in the absence of such vapors. It must not be supposed that a molten magma consists merely of a number of fused minerals mechanically mixed together and having no effect upon one another. Petrographers believe that a molten magma is a solution of certain compounds in others, and that crystallization occurs in the order of solubility, as the point of saturation for particular compounds is successively reached by the cooling mass. Professor Kemp has determined the order of formation of minerals in a solidifying magma. First to form are apatite, the metallic oxides magnetite, ilmenite, and sulfides pyrite, zircon, and titanite. Next, he says, come the ferromagnesian silicates, olivine, biotite, and the pyroxenes and hornblende. Next follow the feldspars and feldspathoids, nepheline and leucite, but their period often laps well back into that of the ferromagnesian group. Last of all, if excess of silica remains, it yields quartz. It results from what has been said that the residual magma is increasingly siliceous up to the final consolidation, for the earliest crystallizations are largely pure oxides. It is also a striking fact that the least fusible minerals, the feldspars and quartz, are the last to crystallize. The classification of the igneous rocks now most generally adopted is made upon a threefold method, according to texture and chemical and mineralogical composition. In the following table, modified for Kemp's, the textures are given in vertical order, while transversely the arrangement is mineralogical, chiefly in accordance with the principal feldspar. The division of the igneous rocks into families is made primarily in accordance with the mineralogical composition, with subdivisions according to texture. This method gives us 5 principal groups. 1. The granite family. This family includes the dark volcanic glass, obsidian, pumice, which is generally known, rhyolite, quartz, porphyry, and granite. 2. The syenite family. The chief rocks included are syenite obsidian, trachyte, phonolite, syenite, and nepheline syenite. 3. The diorite family. There are but 3 important rocks in this class: andesites, dacites, and the diorites. 4. The gabbro family. This includes basalt, which is a name covering many varieties. They are common volcanic rocks and are thrown out now by the most active volcanoes. And 5. The peridotite family, embracing pyroxenite, hornblendite, and, after alteration, the serpentites. The sedimentary rocks are secondary formations. They are formed of the debris of the igneous rocks as the latter have been worn away by the destructive agencies of the atmosphere and water, so that, having been laid down usually underwater, they are almost always stratified, and are formed with rounded fragments, rarely crystalline. The great bulk of the sedimentary materials consists of simpler and more stable compounds than the igneous minerals from the decomposition of which they have been derived. The most useful classification of the sedimentary rocks is primarily according to the mode of their formation. This gives two principal divisions: 1. The aqueous rocks, or those laid down under water, and 2. The aeolian rocks, those which were accumulated on land, which are of more limited extent and importance. The rocks laid down under water form the larger and more important part of the sedimentary series. From the accumulation of debris derived from the destruction of pre-existing rocks, carried in mechanical suspension by moving water, whether waves, currents, or streams, and dropped when the velocity of the moving water was no longer sufficient to carry them, a certain group of the aqueous rocks has been formed. Such accumulations are forming today in all kinds of bodies of water, and an examination of the rocks will show that similar accumulations have been made since the beginning of recorded geological time. Mineralogically, the mechanical deposits are of two principal kinds, the siliceous and the argillaceous. The sorting power of water has been sufficient to separate them more or less completely. Sand, sandstone, gravel, and conglomerate are in the siliceous group, and clay, mud, mudstone, and shale are the argillaceous rocks. The chemical precipitates are locally restricted and not at all comparable to the great masses of mechanical and organic sediments. This arises from the fact that the chemical processes occur in a conspicuous way only around the mouths of certain classes of springs and enclosed bodies of water without outlet and subject to evaporation. Thus, calcareous tufa, oolite, gypsum, and rock salt are alkaline. Geyserite and chert, flint, are siliceous, while bog and lake iron ore are ferruginous precipitates. Limestone, shell marl, chalk, dolomite, and green sand are calcareous accumulations, formed almost entirely by the accumulation of vegetable matter and its progressive though incomplete decay underwater. This decay is of such a nature that the gaseous constituents diminish while the carbon is removed much less rapidly. Consequently, the proportion of the latter substance steadily rises. All the varieties of carbonaceous rocks pass into one another so gradually that the distinction between them seems somewhat arbitrary. From fresh and unchanged vegetable matter to the hardest anthracite, there is an unbroken series of transitions. The three main divisions are peat, lignite or brown coal, and black coal. Aeolian rocks form less of the Earth's crust than do the aqueous rocks, but they have a special importance because of the hints which they often give as to the physical geography of the place and time of their formation. Blown sand, forming dunes, drift sand rock, talus, soil, and loess are of all Aeolian origin. Examined with the reference to the simplest and broadest facts of structure, it will be noted that rock masses fall into two categories: 1. Stratified rocks, and 2. Unstratified or massive rocks. The stratified rocks form more than 9/10 of the Earth's surface, and if the entire series of them were present at any one place, they would have a maximum thickness of about 30 miles, but no such place is known. As sedimentary strata were laid down upon one another in a more or less nearly horizontal position, the underlying beds must be older than those which cover them. This simple and obvious truth is termed the law of superposition. It furnishes the means of determining the chronology of rocks, and though other methods of ascertaining this point are employed, they must all be based originally upon the observed order of superposition. The only case, says Geikie, in which the apparent superposition may be deceptive is when the strata have been inverted, as in the Alps, where the rocks composing huge mountain masses have been so completely overturned that the highest beds appear as if regularly covered by others, which ought properly to underlie them. but these are exceptional occurrences, wherein the true order can usually be made out from other sources of evidence. The stratified rocks which form the land have been changed, at least relatively, from the position which they originally occupied, since the great bulk of them were laid down under the sea. Originally, they must have been nearly horizontal, for this is a necessary result of the operation of gravity, just as a deep fall of snow, when not drifted by the wind, gradually covers up the minor inequalities of the ground and leaves a level surface. So on the sea bottom, the sediments are spread out in nearly level layers, disregarding ordinary inequalities. The displacements to which strata have been subjected after their formation are of two principal kinds. One, in the first kind, the strata have been lifted vertically upward, often to great heights, without losing their horizontality. In some of the lofty plateaus through which the Grand Canyon of the Colorado has been cut, almost horizontal strata are found 10,000 feet above the sea level. Two, more frequent and typical are the displacements of the second class, by which the beds are tilted and inclined at various angles. The double condition of a semi-rigid crust with a fluid strata below, coupled with the phenomenon of cooling and contracting, renders the rocks of the earth susceptible to intensely heavy stresses, and breakage is inevitable, dislocation often occurring. But in all parts of the earth's surface the rocks are to be found in strata, so that when such a break occurs it interferes with the continuity of the strata. Where such is not the case, but the rock merely cracks open without any alteration of the levels of the various strata, it is called a fissure. But when the strain has been vertical as well as horizontal, it is usually so, the result is to change the consecution of the strata. This is called a fault. Whenever the rocks of the earth's crust are subjected to strain, says J.E. Spurr, fractures take place in them as in any other body under similar conditions, and the different parts of the rock tend to move past one another along the fracture planes, seeking to obtain relief from the strain and to accommodate themselves to new conditions. In this movement, one part of the fractured rock mass may move upon the other in any direction, up, down, sideways, or obliquely, according to the conditions, which are different in each instance. The throw of faults varies greatly in different cases, from a fraction of an inch up to thousands of feet. In those of small throw, the plane of fracture is frequently a clean, sharp break, but in the greater faults, the rocks in the neighborhood of the fault are often bent, crushed, and broken, forming a confused mass of fragments. In the present state of knowledge, however, any scheme of classification has an undue appearance of exactness. Radial faults are those in which the principal component of the movement has been upward, downward, or both, though subordinate movements of tilting and rotation frequently occur. Normal faults, also called gravity faults, are those in which the fault plane inclines towards the downthrow side, which forms the hanging wall. It seems best to use the term normal, says J.A. Reid, to cover those faults in which, using the horizontal plane as datum, the hanging wall has dropped relative to the foot. Strike faults are those which run parallel or nearly so to the strike of the beds. Dip faults are, in general, parallel to the dip of the beds, and therefore cross or branch out from the strike faults of the same region more or less at right angles. They are less important than strike faults, having generally a smaller throw and less length. Dip faults do not always follow the dip, and strike faults often deviate considerably from the strike of the beds. And sometimes the fault is neither one nor the other, but midway between the two, and then it is called an oblique fault. A reversed fault, which almost always coincides with the strike of the beds, implies a local compression, for the beds occupy less space than before dislocation. In horizontal faults, the principal direction of movement is horizontal, and in horizontal strata may readily escape detection. In faults of the preceding groups, there is apt to be more or less rotation because of unequal friction and resistance of the walls, but in certain cases this movement of rotation is the principal one, exceeding any movement of translation, and these are the pivotal faults. A thrust is like a reversed fault in that it is the result of compression, and that the inclination or height of the fault is toward the upthrow side, which is the hanging wall, but differs in the tendency to a horizontal position of the plane of fracture, and in the association with violent folding and plications. In his latest work on the subject, B. Willis divides thrusts into the following three groups. Scissors thrusts are those in which the fault plane is independent of any older structures and occur chiefly in the crystalline schists, metamorphic rocks, and granite, and, as a rule, depart but little from horizontality. Thrusts of this kind are developed on a great scale in the southern Appalachians, especially in eastern Tennessee, where thrusts of 20 miles or more have been observed. On an even more gigantic scale, they occur in the highlands of Scotland and Norway, where the movement of translation amounts to 75 miles. Fold thrusts are intimately connected with folds and occur only among folded sedimentary rocks. They may rise by plication and inversion, usually between an overturned anticline and the adjoining synclines. Surface thrusts, as their name implies, are formed at the Earth's surface, where a rigid, gently inclined stratum that crops out of the ground is subjected to lateral compression and thrust forward over the underlying beds. End of section 20.